You know, when we think about drilling deep into the earth, we always picture the drill bit, right? That big metal grinding thing. But for a moment, forget about the steel. The true unseen force that lets us drill for miles, well, it's a liquid. Today, we're going to dive into the powerful science of drilling hydraulics, and you'll see how it solves a problem that seems almost impossible.
So let's just start with a puzzle. Imagine you're digging a hole that's miles deep. Every single inch you go, you're creating this pulverized rock. Engineers call them cuttings. And all that junk has to be removed. But you can't just stop and, send down a giant vacuum cleaner. So how in the world do you clear out tons and tons of debris from the bottom of a hole while the drill is still running?
Well, the answer is a powerful, high-velocity liquid. But it's not just for rinsing things out. This fluid is actually blasted out of nozzles that are built right into the drill bit. It creates these jets that are so powerful they act like a water jet cutter you'd see in a machine shop. They literally help fracture the rock, they clean the bit's teeth, and they start lifting all that debris away, all in one go. It is an aggressive and absolutely essential part of drilling.
And this really gets us to what you could call drilling's dirty secret. I mean, all the glory goes to the drill bit, right? It's the thing breaking new ground. But the real unsung hero of the whole operation is a system that's designed to get rid of all that broken rock. Because, let's be honest, without an effective way to handle the mess, the entire job would just grind to a halt.
So what does this system actually have to do? Its to-do list is, well, it's incredible. It is a multitasking superstar. It has to clean the bottom of the hole for the bit, it has to scour the bit itself to keep it sharp, and oh yeah, it has to haul tons of rock cuttings for miles back up to the surface. And as if that's not enough, it's also managing these immense underground pressures to prevent a total disaster, and it even helps power the drill itself.
Really, the best way to picture all this is to think of it like the circulatory system of the entire drilling rig. The drilling fluid is its lifeblood. It's in constant motion, delivering power and carrying away waste. And just like in any living thing, if that circulation stops, the whole system dies. It's that critical.
Okay, so let's follow the journey. It all starts up at the surface, in these big mud tanks. Then, these massive high-pressure pumps force it down the inside of the hollow drill pipe. It blasts out of the bit at the bottom, does its job, and then begins the long trip back home. It flows up through that little gap between the pipe and the wall of the hole, that's called the annulus, and it carries all the rock debris with it. Back at the surface, the cuttings get filtered out, and the clean fluid goes right back into the tanks to start the whole trip over again. It's a closed loop.
Now, we've been calling it a fluid, and on the rig, everyone just calls it mud, but that nickname really doesn't do it justice. This stuff is a highly engineered, non-Newtonian substance. What does that mean? Well, in simple terms, its thickness, its viscosity, actually changes depending on how fast it's moving. It's designed to be thin like water when it's being pumped at high speed, but then to thicken up almost like jello when it slows down. And that is an ingenious property because it's what suspends all those rock cuttings and stops them from just falling back down the hole when the pumps shut off. Every single property is precisely controlled.
So all of this engineering leads us to the first massive challenge, pressure. You got to remember, deep underground, you're not just drilling through solid rock. You're basically entering a natural pressure cooker. And that drilling fluid, that mud, becomes your #1 tool for playing a very, very high-stakes game of pressure management.
And the way they measure all this is with a concept called equivalent circulating density, or ECD. It's actually pretty simple when you break it down. First, you've got the sheer weight of that miles-long column of fluid just sitting there pushing down. That's your hydrostatic pressure. But the moment you start pumping it, the friction of all that moving fluid adds even more pressure. Add those two together, and that total pressure that the rock is feeling, that's your ECD.
And as this gauge shows you, it is a balancing act on a razor's edge. Seriously, if your pressure is too low, you're in the red. The natural pressure in the rock is going to push back, and you get a dangerous kick or even a full-on blowout. But if your pressure is too high, you're in the other red zone. You will literally crack the rock formation, and all of your expensive drilling fluid just leaks away into the ground. The only safe place to be is that tiny little green window right in the middle. Okay, so let's say you've nailed the pressure. You're in the green. But that's only half the battle. Now comes the second huge job, the brute force labor of actually cleaning the hole. We're talking about the long haul up, a vertical conveyor belt that has to lift tons of rock, chip by tiny chip, for miles on end. This little diagram breaks down the physics for just a single rock chip. You've got gravity, which is constantly trying to pull it back down. The fluid's buoyancy gives it a tiny little lift. But the real workhorse here is the drag force from the mud flowing upwards. That upward force has to be strong enough to beat gravity and carry that chip all the way to the surface. Now, just try to imagine that exact battle happening for millions and millions of particles, all at the same time.
So how efficient is this whole process? Well, they measure it with something called the transport ratio. And here's the part that might surprise you. Because of gravity, those little cuttings are always slipping backwards through the fluid that's trying to carry them up. It's a constant struggle. Get this, if the cuttings are moving up at just half the speed of the fluid, that 50% ratio is actually considered a success. That's considered adequate. It just goes to show you how incredibly difficult this job really is.
Now, everything we've talked about so far is already super challenging in a straight vertical hole. But here's a question. What happens when the well starts to bend? When it goes sideways for thousands of feet, like so many modern wells do?
The second that well turns sideways, gravity really starts to win. Instead of just slipping straight down, the cuttings start to settle out on the low side of the pipe. And if you're not careful, they form this dense pile, what's known as a cuttings bed. This can completely block the flow of your mud, and even worse, it can trap your multi-million-dollar drill string. That is a catastrophic failure.
So you've got all these competing challenges, right? Pressure management, cleaning the hole, dealing with vertical versus horizontal wells. It all comes down to what is essentially an optimization game. Engineers are in a constant battle to find that perfect sweet spot between drilling fast, drilling safely, and of course, drilling cheaply.
Every single minute of the day, engineers are juggling these impossible trade-offs. You see, pumping faster cleans the hole better, but it also dangerously jacks up the pressure. So, okay, maybe lower the pressure. That's safer for the rock, but then you might not be able to lift the cuttings out. It's always a compromise. Drill too slow, and the daily cost of the rig will absolutely destroy your budget. But drill too fast, and you risk a disaster that's even more expensive, like getting your pipe stuck.
And this chart, this cost per foot curve, it really sums up the whole economic problem. See, as you increase your fluid speed along the bottom, your cost per foot goes down. That makes sense, right? You're drilling faster and more efficiently. But that only works up to a point. If you go too fast, the pressure starts rising, you start having problems, and your costs just skyrocket. The entire game, the goal for the whole operation, is to drill right there at the very bottom of that curve, the perfect sweet spot.
So that's it. That's the core of hydraulic optimization. It's this constant, delicate balancing act. It's all about using the horsepower you have from your pumps to drill as fast as you possibly can, and therefore as cheaply as you can, without ever crossing that dangerous line where you fracture the rock or lose control of the well.
And after all the complex physics and the incredible engineering, the final objective couldn't be simpler. It's right here. Maximize the drilling rate or to minimize the drilling cost. That's the bottom line. That's what it all comes down to.
Look, we are constantly pushing the boundaries, drilling in more and more challenging places, from the deepest parts of the ocean to the most complex geology you can imagine. But in every single case, the fundamental puzzle is exactly the same. It's that simple, brutal act of moving fluid and rock. So the real question is, what's next? What kind of innovations in fluid dynamics and real-time data are we going to need to unlock the next frontier?